Okay, welcome to the final video on the exponential distribution, which in which we're going to look at the something called the memoryless property, and then we'll try and sort of put it together with a few kind of questions to kind of sum up all the work that we've done. So there'll be a chance to have a practice today, and then sort of thereafter, I think we should be able to just set some problems by attaching a few files, that kind of thing. But just before we do so, we've just kind of got a kind of problem that I sort of posed part-way through the last video, and you may have already had a go at this. If you haven't, then I'll just draw your attention to it. Flick this round. Just wait for it to focus. There we go. So I sort of posed this a little bit last time round. And I said that when we did this, the big proof of the expectation, or the mean, and the variance or the standard deviation, I said you don't need to do that substitution that we did to kind of sort of standardise it. So I kind of, if you haven't had a go, I'm sort of offering this to you now to kind of, well, either now or just at some point soon, if you want to kind of pause and have a go at this. You will need to use obviously your knowledge of integration by parts, but this is a kind of question that actually they can ask on the specification, and I think they have been known to ask this, so it is something that you need to be able to do. As I've said all along, it's going to really help you with the single maths part of the course, so yeah, I'd thoroughly recommend giving it a go. And look, I mean, if you need to use the notes from last time, by all means do, although it essentially is, it's kind of the same thing, barring the substitution. So, it'd be nice if you can really give it a go. If you think you're at the stage where you can do it without looking at the notes, that would be brilliant. But we'll just park this for now and leave that be. And instead, we're going to have a look now at something called the memoryless property, like I say. So, quite a defining feature, this, of the exponential distribution. Okay. The main idea about this is that, and again, it's statistics, so it's a model. And it won't necessarily be absolutely perfect in real life, but theoretically, when we deal with the exponential distribution, what's incredibly special about it is no matter how long you've waited for something, this then doesn't affect the probability of waiting for a next sort of however long, whatever next period of time you choose. And I'll kind of use the email example just so we've got the consistency there once again. But it's a very, very bizarre thing to sort of get your head around at first. But then again, the exponential distribution, the exponential function itself is bizarre. You'll recall from year 12 when you first meet the exponential function that it's got all sorts of special features, not least the fact that when you differentiate it, you get the function back itself. The only function in the world where that happens. If you zoom in on the exponential function, it looks just like an exact replica of itself. So yeah, it is by the very nature of it, very special, and it's got these special features. And this is just kind of another virtue of that, really. So, as we said, let's go back to the context of emails, which we've maintained throughout. So if we imagine waiting for an email again, and we're thinking in exponential world here, not Poisson, so it's kind of the time that we wait until the email arrives. And naturally, we'll assume that we are starting at time t equals 0. So this is kind of a bit more of a thorough explanation about what we mean by this memoryless property. And what we mean is that no matter how long we have waited for that email to arrive, it's called memoryless because it essentially, in terms of probability at least, it forgets this. So it's as though that waiting time just hasn't happened at all. Feels a little bit magical, doesn't it? So like, we're starting from fresh each time. Okay, and when you start to think about it, you can kind of appreciate, okay, maybe there are circumstances. I think there's a classic one of a sort of shopkeeper, that if you are the owner of the shop and you're at the checkout of a corner shop, say, and it's been 10 minutes, no customers have come through the door. That doesn't, although maybe perhaps instinctively, maybe this is the kind of the human nature to sort of we kind of not necessarily gamble, but we sort of misinterpret statistics. It's kind of there's a sort of, not a syndrome, but there's a thing with the national lotteries, and there were I don't know, if you, something to do with, you convince yourself if you pick the same numbers each time that it's going to come up, or this kind of thing. But you might well convince yourself as the shopkeeper that the fact that you've waited for 10 minutes. Oh, that's right, sorry. People think that if they've selected a bunch of random numbers for the lottery, that they're perhaps more likely to win than if they just picked, 1, 2, 3, 4, 5, 6, 7, 8, which of course is just as likely. But yeah, with the shopkeeper thing, you could imagine that you've waited for 10 minutes, no customers, and the human nature thing might tell you that, you're more likely to get one in that next minute, just because you've waited 10 minutes and had nobody, when in fact it may be the case that you're just as likely to get somebody in that next minute as you were in the very first minute. Nothing's changed. So you might have some counteract a few sort of ideas to that, but that's the sort of the general idea, if you see what I mean. However, being further mathematicians, I'm hoping that you won't just kind of take my word for it. I'm hoping that you'll want some sort of evidence to back this up, rather than just saying, well, this is true of the exponential distribution. So what are we saying? We're saying that here, the probability that, let's call it y, the probability of that being greater than some extra time on top of the elapsed time already. So let's say we've got time lowercase t. If I sort of add an s onto that, which way around? No, let's do it the other way around. Let's say we've s times elapsed, and then we add an extra bit of time on t. What's that probability given that we've already had s amount of time elapsed? And what I'm arguing is that it's going to be the same as this. Okay, so the fact that we're given that y is already greater than or equal to time s, so we've already waited s amount of minutes, for example, what's the probability of having to wait s plus this extra time t? Well, we're saying that it's just going to be the same as the probability of it being this extra time t. Okay, the fact that we've waited s minutes becomes irrelevant. It plays no part in the probability. So let's consider y then. Okay, so the probability that y is greater than or equal to s, which, by the way, this is quite an interesting sort of note. This is often we've actually come across this, I think, or in some guys at least we have. It's often called the survival function. Exponential function obviously comes up a lot in real life nature and things with exponential growth, and so this is a very sort of real world topic, and so it might be something like, this might be a bit vague, but will somebody live, obviously you have to do some modelling to get to this stage, but will somebody, how likely would they be to live over 90? Kind of will this phone battery survive? Will it last? you know, will this particular sort of breed of animal last in the coming years, or will it go extinct? This kind of thing. So, and that's simply because it's will it survive over this amount of time, essentially. So it can often be called the survival function, which gets used a lot in sort of natural modelling in the real world. And if we use the knowledge that we have already from the previous work, then we know it's continuous. Okay, so that's just going to be the probability that the probability that y is less than or equal to, makes no difference because it's continuous, to s, and that equals 1 minus, now if you recall, this is the cumulative distribution function, so you could also write this as capital F of s, and if you remember the cumulative distribution function from the other video is determined by 1 minus e to the negative lambda, in our case lambda times s. And of course the 1 minus the 1 will cancel, and then just be careful with our signs. So we get this, which is the survival function. And you're very well within your rights to use this in all your kind of future questions. If you appreciate this idea and you want to skip from that to that immediately, there's absolutely no harm in you doing this. And in all honesty, when we come on to some questions shortly, I'm going to be a bit stuck in terms of I don't know which way is best to illustrate this, but certainly this can be a very quick way to cut a couple of corners and save having to do this sort of thing each time. But it's really what works best in your mind. Okay. So that's not working, sorry. So let's actually try and get to work to show this. Let's take what we actually referred to earlier. Let's try and roll with this a little bit. When you're trying to do stuff, calculations that are based on conditional probability, the probability of A given B, then we need to really, I think it's just, I've always stressed, when I did this in year 12 further maths, the importance of appreciating that this means the intersection of both. There's the intersection. So it's the probability of both things being true out of the probability of the second thing being true, the thing that we are given to be true. And really all this is, I'm sure you're probably well aware of this, you don't have to illustrate it this way, but I don't know, if these are people that like coffee and these people that like tea, you can quickly show this in a Venn diagram, just put some numbers in, and you say what's the probability of someone liking coffee given that they like tea. Well, you're in the tea section because I've told you that they like tea, so instead of being out of 8, 9, 10, 11, it must be out of 8, and the probability of them liking coffee given that they like tea must therefore be 3 out of 8. You can see it straight away. And what I'm trying to sort of illustrate here is that this is the probability of them being in the intersection. They've got to satisfy being both in coffee and tea, but it's divided by the probability of them being in tea. Sorry, that's not quite, almost there. Oh no, sorry, that would have worked, yeah, as would that, I think. Slightly messed that up, but hopefully you got the idea there. I think that was right. Okay. The intersection divided by just the latter bit itself, the bit that you're given. That was due to be lovely and clear until I confused it. Anyway, so it was right first time. Let's kind of progress with this and think carefully about what this actually means. And I'm going to leave this first bit to you for 10 seconds or so, because I'd like you to not worry about the denominator, but just have a look at the numerator and think, how can I simplify that? What does that actually mean? So try and actually interpret it and get your head around it. Okay. I mean, you may well have just tried it with some numbers, but kind of hopefully the intuition just takes you to the point where you realise, oh, hang on, the probability of it being, you know, and we're assuming these are positive values, the probability of being greater than or equal to s plus t intersect with the probability of being greater than or equal to s. Well, the first one overrides the second. It's just equivalent to the probability of being greater than or equal to the first one, s plus t. Okay, there's got to be, if this s plus t is greater than s, then the probability of being bigger than this and bigger than this, it's like saying what's, you know, you've got to be bigger than 10 and also bigger than 8. Well, you have to be bigger than 10. It's the only way it can satisfy both. So that's the numerator sort of simplified slightly. There's the denominator just as it was. Okay. And since we've got this in greater than or equal to format, it's in the survival function format from before, so we can just skip straight to using our result if we want, which is e to the negative lambda s, but that depends on what the time frame is, which in the first instance in the numerator is s plus t. So actually our numerator, when we write it in terms of exponentials, will be as follows, and the denominator should just be as straightforward as it was previously. Okay, and again I'll just give you sort of 10 seconds just to have a think about how to simplify the following. Just whilst you finish that off, it's bugging me now. I'm going to correct this one. Don't know why I sort of changed my mind there. It's perfectly correct as it was. Okay, so it was right first time. Right. So using your kind of laws of indices and expanding the brackets out and so on, you should realise that the e to the negative lambda s's will cancel, and you'll be left with e to the negative lambda t, which itself is the survival function, just with s replaced with t, and so it is this probability of y being greater than or equal to t, which is exactly what we said it would be, or at least what we were trying to show. So actually, look, we started with this, the left hand side, and we've ended up with the right hand side, so it must be true, and we just did it with general amounts of time, s and t, so therefore we can say we have proven that it is indeed memoryless. And there's a joke that does the round that you might possibly see at some point that will now make sense. And a kind of final point to make on this one is that the exponential distribution is the only distribution which is memoryless. It actually characterises it itself. Okay, and this is something that perhaps not the proof per se, although again it was just a nice sort of dip into stuff that you're going to have to know anyway with statistics, about intersections, about conditional probability, about even just simple things like the substitution from here to there, as along with the laws of indices. I mean, every step was useful anyway. But certainly the result is a really common one that they like to test on the exams, and it is very, very straightforward when you spot it, and when you don't, people often make a hash of it, and it's surprising how many people do miss it, which is a surprise really. So I'll just keep that paper close by in case we need it. We'll have a look at a problem. So here's our first problem that we've actually come on to, and here it is. Hopefully there you can just about see that. So we've got an LED light bulb. We're told it's exponentially distributed, and it has a mean time of 5,000 hours. Okay. What is the probability density function for x, the random variable for the life expectancy of the bulb, in hours? Okay, well, if we know, if we call it just say it's x, so we know that x is exponentially distributed. The mean of the exponential distribution is 5,000, but don't forget that's 1 over lambda. Sorry, the mean is 5,000, so lambda itself must be the following. So that must be the number of bulbs that die every hour, and you'd hope it's low. Okay, so that makes sense, and you would hope that this is high, which it is, which is the length of time, the mean time in between light bulb failures. Okay, so that makes sense for our setup, hopefully. And it asks for the probability density function. Okay, so lowercase f of x is equal to. By the way, do feel free to pause this and have a go. I'm going to sort of run through a few of these, and then perhaps on this lesson or the next lesson, somehow I'll try and attach, or on Blue, I'll try and attach some questions to have a go at. So let's see. We've got. Well, we know this. We've done it before. It's lambda e to the negative lambda, in our case x rather than t. So lambda we know is 1/5000. So that's lambda e to the negative lambda, and our variable is x. So we can write that as negative lambda's 1 over 5,000, and there's my x. Let's try and remember to set it up in the correct way, and that's all it asked for really, the PDF. Okay, next question B. What's the probability that it lasts for more than 4,000 hours? Now we've got so many different ways that we can approach this that it's the choice is really yours now. So we want the probability that x is greater than 4,000. So, I mean, we could just jump straight in with the survival function since we've just done that. We could think about this kind of idea, although once again, alarm bells should be slightly ringing because, as I've referred to this as an improper integral, so we shouldn't really be using infinity as one of our limits. But we could kind of think about it as 4,000 up to a certain variable. And just think about that variable as it tends towards infinity, and think about that as f of x dx. And we can just stick this into the calculator and see what we get. That's kind of sort of nice. Oh, hang on. Sorry. Yeah, that would work, wouldn't it? Okay, so that's not too bad. But obviously we're going to struggle to put infinity into the calculator, so we could do 1 minus this, which is probably a bit nicer. That's quite a nice way of thinking about it. Or we could just take the work that we've done previously, like I say, use this idea of the survival function and just go, well, we know that the probability y is less than or equal to s is this, bit in brackets, so it's just going to be 1 minus that. And it really is up to you. I know a lot of students in previous years they kind of they learn this bit well, the cumulative distribution, and so they know to them 1 minus that. It's kind of your choice, it really is. I kind of feel a bit stuck now as to what to do. Let's get used to some of the terminology and the language. Capital F is the cumulative downwards from the lower end up to 4,000. So I'm kind of doing the long-winded way here. So therefore it's going to be 1 minus e to the negative lambda x. But of course I could have just written that straight away using the survival function. And let's just simplify the 4,000 divided by 5,000. And either way, we should get the following, 0.449-ish. Okay. Part C then asks, oops, sorry, let me just box this off. Part C asks, sorry, what's the probability that it lasts more than 10,000 hours? Well, it's much the same, is it not? We can kind of have a guess, first of all. What would you expect it to be? Would you expect it to be a higher or lower probability than the previous answer, that kind of thing? Just so that your intuition, kicks in. And that usually serves you well, in any exam question, but some more than others. If you can gain a feel for whether it's more or less than something as simple as a 1 minus, and there are going to be a lot of those kicking around in this topic, could stuff you up and get you the wrong side, if you like, of where you should be. So a bit of intuition should hopefully tell you that it's going to be less. And we can go for sort of any of these approaches that we've done before, but let's just do it a kind of more succinct way this time and go straight in with the survival function. So it's going to be e to the negative 10,000 over 5,000, which is negative 10 over 5. And so with any luck, e to the negative 2, and even if you just, as I've tried to sort of suggest throughout, if you can have that exponential graph in your head at all times, then you'll instantly know that that's going to be less than the previous one, and indeed it comes out to be 0.135. It's 3 significant figures. Okay. Now we're on to part D, which says a bulb has already lasted 5,000 hours. What is the probability that it will last more than 9,000 hours in total? And this really isn't a particularly hard question when you bear in mind the work that we've just done, because we're saying what's the probability that x will be greater than 9,000 given that x is greater than 5,000. Okay, and we've talked about the memoryless property, and it's really a case of if you miss it in the exam, well, you've missed it. I mean, it should be they're going to have to make it relatively obvious, and the fact that it's already lasted 5,000 hours, that's got to be the giveaway when it says it's an exponential distribution, so you have to spot this straight away. This is the same as saying, what's the probability of it lasting more than 4,000 hours? Okay, it's the same thing. The 5,000 that have already happened, that you've waited for and nothing's happened and it's still survived, great. Chance of it lasting over 9,000 overall, really it's just saying what's the probability that it lasts this next 4,000 hours, and funnily enough we've already done that, so happy days, we can just take that answer straight away, and there we go, we're sorted. Should you've forgotten, I suppose it's not sort of out of the question for you to then do what we said before. It's going to be a lot more hassle, and you're essentially going to almost prove this, but we're going to have actually specific values in. So you could go at it like this and say what's the intersection of it being greater than 9,000 and also greater than 5,000. Well, that's the probability that it's greater than 9,000. Slightly running out of space here, sorry. And if you work out each of those individually, so what's that, e to the negative 9/5 divided by e to the negative 1, is that, when you actually pop it all in. And just for completeness, let's have a look. E to the negative 9/5 over e to the negative 1. Oh, and would you look at that, 0.449 once again. Okay, just for reassurance. Okay, so it's the same. So even if you kind of do miss it, as long as you're precise, you'll get there in the end. But it's much quicker, and not going to be worth a huge amount of marks, but it's marks that really we should be getting. So yeah, some of the questions, like I say, fairly sort of trivial if you know the formulas, but all the work that's gone into this should mean that you're kind of ready for the hard questions and the twists, and things like the proofs will be much more natural to you, and you don't necessarily have to memorise them if you're confident with your techniques and all the work that we've done to date. So just pop on a small bit of background music just whilst I set up the next part. I said we'd look at a few questions in this section. Okay, won't necessarily write all of these down, but well, no, we will. We'll just run through a few kind of quickly for the sake of it, to kind of look at different ways that this could be tested. So we could have, just kind of for the first question, random variable x, and let's say it has an exponential distribution. With parameter, remember that's not the mean, it's the mean for the Poisson but not for the exponential, parameter 0.5, and we could be asked to find the probability that it lies between 1 and 2. So, just invite you to have a quick go. You might end up having to pause the video because I'll jump in a moment. Okay, and I mean, like I've said, there's so many ways that we could actually look at doing this. Here's just one possible way. We could just say, okay, I understand about continuous distributions, so the probability of it lying between 1 and 2 means I can just integrate the PDF, which is lambda e to the negative lambda x, since x is our variable. And if they wanted to show you that, then, or if they wanted you to show that, then we could integrate it and see that the half will cancel out when you divide by a half, or you could of course just type this straight in on the calculator, which is probably what they're going to expect unless they pop a variable in, a letter in of some kind, just to kind of throw you there. But if they wanted you to leave it exact, the calculator might not spit out in this form, so perhaps that would be how you'd have to leave it, or perhaps a little bit more tidy than that. This is 1 over root e, and then minus 1 over e. So of course we know that they could ask you to do that, or maybe even as a single fraction. Perhaps you'd have to cross multiply or rationalise the denominator. You get the idea. So there's one possible way of tackling that question. Okay, let's have a look at a second question. I'll write it out, and then you can feel free to have a go, and I'll kind of come back to the page in a minute or two. Oops, sorry, the page is a bit twisted there. Okay, you've probably spotted the not very funny little joke here. It's the same question. So, invite you to have a go, but this time try and do it some other way. Should get the same answer. How else could we think about doing this? Okay, well, this is one way that I was thinking about it. Of course, it's all the same in reality. It's just a different setup, different way of sort of writing it out. We could go with the cumulative distribution. So the idea that probability that it lies between 1 and 2 is this idea. Remember, we have to not be getting this bit wrong. Okay, that's come up in year 12 further maths, and probably will do in single at some point as well. So if we use that idea, then we can write that as capital F of 2 minus capital F of 1, and that's the cumulative function, which we know is 1 minus e to the negative lambda t. So in this case it's negative lambda is 0.5, and I said t, but I meant x, so 0.5 times 2 gets you 1. So that's f of 2 minus f of 1 is going to be 1 minus e to the negative lambda, so negative 0.5 times by x, which is 1, so that's going to be negative 0.5. And we're pretty much back at the same point that we were at, because the 1's will cancel, and we get this as we had before. Okay, just like we had last time. Okay, so that's kind of quite nice. Oops, sorry, let's get that on the page. Yeah, let's have a look at maybe one third question that we could be asked. I will make this one slightly different, I promise. So, see how you get on with this one. Note, on all of these I have put the parameter I've given you, but they may well try and confuse you by giving you the mean of the exponential distribution, so just be alert to that. Okay, you want to have a go at that one? Okay, you may well have just paused the video instead of using that time. So let's have a quick look. Hopefully this wasn't too tricky. So the mean of x, e of x, is a half, 1 over lambda. We know from our proofs from one of the other videos that the variance will then be the square of this, 1 over 4 or a quarter. Or, I mean, we pretty much said it at the time, the standard deviation of x, well, it'll be the same. It'll be the square, the positive root of a quarter, or in other words, it'll just be the same as the mean, as it was in the Poisson distribution. So therefore, what we're actually after when we say one standard deviation either side or within the mean, lies within one standard deviation of the mean, is we're essentially saying a half less than this and a half more than this. So it's the same as saying, doesn't matter if we put this in the equal to bit in or not, it's essentially the same as saying that, and then how you go about that is kind of up to you. You could go for the differentiation approach, integration approach. You could pull out the 2 if you wanted. Again, probably a sensible idea if they ask you to give it in an exact form. Okay, again, you need to be really comfortable and fluent practicing your integration with exponentials and realise that the 2 will cancel by the dividing by 2, or negative 2 I should say. Stick in 1 and you get negative e to the negative 2, stick in 0 and you get 1. Let's put those the other way around. So we get that. If it asks for an exact answer, we're going to have to do it that way, otherwise we could just type this straight into the calculator. Okay, so there's kind of a few sort of quick questions, which all the work that we've covered now should hopefully make this much more understandable. I'm going to finish with one final problem for everyone. Okay, and this is one that I quite enjoy actually. I think this is quite a nice one, and hopefully now we've got the knowledge to be able to do this. So the question is as follows. What is the median of the exponential distribution let's keep it general, with parameter lambda. And also, what about the interquartile range? So we're looking for a general expression for each of these. So I mean, you can pause the video. I'll just give sort of a few minutes anyway for you to kind of make a start on that, and then I'll come back to the page in a moment. Okay, and I'll go through it in just a sec. For anyone who just wants a hint, and then we can kind of pause it again after that. The way I'm going to look at it is thinking about, well, it really is, you have got a choice here, is thinking about the cumulative function and the idea of median, which we have talked about in Year 12 further maths. But you could use the PDF, it's really kind of your choice. Okay, let's have a look. So first of all, let's just have a look at this setup. So it's x follows an exponential distribution. The parameter is lambda. So if that's true, then what do we have? We have that the median of x is a specific value, lowercase x, such that, and this is the kind of the fundamental idea, whether you use the PDF approach or the CDF, which is what I'm going to use, or even the survival function. This is the fundamental idea, okay? So if you didn't get to this stage or something equivalent, then feel free to kind of pause it and take it from this point onwards. But I'm just going to continue now. So the cumulative function, you know, if you go from whether it's time or whatever it is, but the initial time up to point x, which is our median, you'll sometimes see this is written as an m, which is understandable, f of m, then it must equal half of the probability. So it needs to be really kind of fluent in your own mind that what capital F of x means, and it's 1 minus e to the negative lambda x. And so all we need to do is solve this, or rearrange it to make x the subject. Okay, solve for x, essentially. And this isn't too hard as long as we're not too scared of it, so a bit of rearranging gets us to this. Okay, and that takes us to, if you think about this as 1 over e to the lambda x, and this is 1 over 2, that makes it clear that e to the lambda x must be 2. But again, you can use as many steps as you wish to get to that stage. What can we do next? Hopefully you're thinking that we could take the natural log of both sides, as follows, and then all that's left, all that remains is to divide through by lambda, and we get our answer. Okay, that wasn't too bad. So let's move on to the upper and lower quartile, which if you were struggling on this one, then you may well be able to do now, but it's going to be much the same idea. So upper quartile of x, often called Q3, because it's like the 3/4 mark, and sometimes the median, if it's not called M, can be called Q2, because it's the kind of second out of 4 marker. Anyhow, upper quartile of x is x such that this is true. So I'm trying to make sure the setup is clear for a reader, rather than just diving in with calculations. And it must be true that cumulatively from the bottom upwards it takes up 75%, or 75% of the data, or the probability is kind of used by the time you get up to this median. Okay, or in other words, to put it more precisely, the probability of it being x or less is 75%. So that gives us the following. Well, let's just speed through this because this is very much the same as it was above. Is that correct? What have we done there? Oh yeah, sorry. Just getting ahead of myself then. Okay, well done if you got that for the upper quartile. And moving on to lower quartile, which again we know it's just going to be the same idea. And I'm really kicking myself now why I didn't just call this M or Q2 and why I didn't call this one a Q3 and this one Q1, because now I've got various different things for what I'm saying x equals, which is a little bit poor really. And I've clearly not used pencil to go back and rub that out, but oh well. Lower quartile of x is lowercase x such that at least I've established what I'm saying x is each time for each scenario. So it's such that this is true. So let's go through the process just for one last time. That'll be the reciprocal of 3/4. Take the ln of both sides, and then we're there. Now whether or not you want to, or whether or not you get a question, sorry, which is about the lower quartile, they could easily just ask, such that I don't know, 72% of the data or 23% of the data lies below it. It could be worded in a slightly different way, and it essentially is the same kind of calculations. So let's just finish off by saying that the interquartile range of x is the upper quartile of x minus the lower quartile of x, which is our ln of 4 over lambda from earlier, minus our ln of 4/3 over lambda that we've just arrived at. And it's going to have a common denominator, so that makes life easier, and now we just need to do ln of 4 minus ln of 4/3, which means, well, think about, we know our laws of logs hopefully, so we get ln of 4 divided by 4/3, which is ln of 3. So quite a nice result in the end, and of course we could then work that out with any value of lambda whatsoever. So that's the end of the kind of teaching side of exponential distribution. Been a huge amount of work that's gone into that, so go back through it and take your time. I suggest, and I'll probably put this on Bloodle as well, use the Caboodle, the online textbook, use the work solutions that I've put onto Bloodle, and definitely practice those proofs as well, if nothing else. Apart from just learning the proofs, it'll help you with kind of instant recall of what the formulas are, and just have a go at some of the questions is what I'd recommend. It's not complicated. I will try and attach some questions that are kind of related to this onto the Bloodle as well. Okay, but yeah, I think that's a wrap for exponential distribution.